Alright, here is your forces practice quiz. I want you to use what you learned in the forces unit to answer these 5 questions. So go ahead and pause the video and give them a shot. And now one thing I like to do is I like to give away the answers right at the start. So here are the solutions to each of the questions. Now let's figure out how I got these answers. We'll start with question number 1. In this question, we are told that a rocket is accelerating up at a rate of 10 meters per second squared. If the rocket's engine provides a thrust force of 100 newtons, we want to figure out what is the mass of the rocket. Now the first thing I want to do is draw a free body diagram. So I draw a point to represent the rocket, and then we know the force of gravity is pushing down on the rocket, and the thrust force is pushing the rocket up. We also know the net force would be directed up because the rocket is accelerating up. The next thing we want to do is write our Fnet equation, which would be the sum of all the forces acting on the rocket. So we have Fnet is equal to the thrust force minus the force of gravity. Remember, the force of gravity is negative because it's a vector that points down. Because the rocket is accelerating, we can replace Fnet with ma. We can replace the thrust force with 100 newtons, and we can replace the force of gravity with mg. And now we want to solve for the rocket's mass. So let's move all the terms that have the mass variable onto the left side. Now all we need to do is pull the mass out as a common factor, and then rearrange and isolate for the mass. And now we can plug in our values and solve. And what we find is that the mass of the rocket is about 5.1 kilograms. And that's the answer to our first question. Now let's move on to our second question. Here we have an astronaut with a mass of 50 kilograms who weighs 300 newtons on a distant planet. And we want to know what is the acceleration due to gravity on this planet. And now this is a super easy question if you can remember that an object's weight is equal to mg. And now with this equation, we can just rearrange and isolate for the acceleration due to gravity. And we see that g is equal to the object's weight divided by its mass. So we can plug in our values and solve. And what we find is that the acceleration due to gravity on this planet is 6 meters per second squared. And that's the answer to our second question. Let's move on to our third. In this question, we have boxes A and B, which are connected to a pulley. Box B is 5 kilograms, and when the boxes are released, it accelerates down at a rate of 2 meters per second squared. And we want to know what is the mass of box A. And the first thing I always do is draw my free body diagrams. We will need one for box A and another one for box B. For box A, we know the force of gravity is pushing down on it, and the tension force from the rope is pulling back up on it. And we know that the net force will be directed up. I know this because when the boxes are released, box A is going to be pulled up, so it will accelerate up. Now let's look at box B. Again, the force of gravity is pushing down on it, and the tension force from the rope is pulling back up. And we know the net force will be directed down, because when the boxes are released, box B accelerates down. And now the most important thing that you have to recognize when answering this question is that the tension force for box A and box B is the same. And now that we have our free body diagrams, let's move on to our Fnet equations. We will need one for box A and another one for box B. For box A, we have Fnet is equal to the tension force minus the force of gravity. Box A will be accelerating, so we can replace Fnet with ma, and we can replace the force of gravity with mg. Now let's look at box B. Here we have Fnet is equal to the tension force minus the force of gravity. Since box B is accelerating, Fnet can be replaced with ma, and of course the force of gravity can be replaced with mg. And now what I'm going to do is I'm going to isolate for the tension force. And the reason I do that is because the tension force is the same for box A and box B. So I can take this value for the tension force in box B and plug it in to the tension force in box A. And when I make that substitution, I get this equation. Now remember, we want to solve for the mass of box A. So I will take all the terms that have the mass of box A and move them to the left side. And now all I need to do is rearrange and isolate for the mass of box A. And when I do that, I get this equation. And you can see, we know the mass of box B, we know the acceleration of box B, we know the acceleration due to gravity. What we're missing is the acceleration of box A. But remember, box A and box B are connected by a rope and moving together. That means their accelerations have the same magnitude, but will be in opposite directions, because box A is accelerating up and box B is accelerating down. And since box B is accelerating at a rate of negative 2 meters per second squared, box A is accelerating at a rate of positive 2 meters per second squared. And now we have everything we need to solve for the mass of box A. All we need to do is plug in our values. And when we do the math, we find that the mass of box A is equal to about 3.3 kilograms. And that's the answer to our third question. Now let's look at our fourth question. Here we have a 2.5 kilogram box, which is being pushed up a ramp with a 30-degree incline. If the person is pushing with a force of 25 newtons, and the box is moving with a constant velocity, we want to know what is the coefficient of kinetic friction between the ramp and the box. Now the first thing we want to do is draw a free body diagram. But what you need to remember is that we're working with an inclined surface. So we need to draw our x and y axis tilted like this. The next thing you need to do is draw the force of gravity vector pointed straight down. And don't forget the angle of the incline, which goes between the force of gravity vector and the y-axis. And now because the force of gravity vector is at an angle, it can be broken up into an x and y component. So we have FGY and FGX. Now that we figured out the force of gravity, let's draw our other forces. So we have the pushing force, the normal force, which always has to be perpendicular to the surface, and we have the kinetic friction. Now that our free body diagram is complete, let's move on to our Fnet equations. And now we have forces acting along both the x and the y-axis. So we need to use an Fnet x equation, which would be the sum of all the forces along the x-axis. So we have Fnet x is equal to the pushing force minus the x component of the force of gravity minus the kinetic friction. And now we were told that the box is moving with a constant velocity. That means we can replace Fnet x with 0. And then we can replace the pushing force with 25 newtons. We can replace the x component of the force of gravity with mg sine theta. And we can replace the kinetic friction with mu k n. Now you might be wondering, where did I get mg sine theta from? Well, if I use vector addition to add FGY and FGX tip to tail, the resultant is the force of gravity. And with that, we form this right-angled triangle. Now I can use trigonometry to solve for FGX and FGY. Let's start by using sine theta, which is equal to opposite over hypotenuse. The opposite side is FGX and the hypotenuse is FG. Now I can rearrange for FGX and I can replace the force of gravity with mg, and we see that FGX is equal to mg sine theta. Now let's use cos theta, which is equal to adjacent divided by the hypotenuse. The adjacent side is FGY and the hypotenuse is FG. We can rearrange this and replace the force of gravity with mg, and we see that FGY is equal to mg cos theta. And that's how you find the x and y component of the force of gravity when you're dealing with an inclined surface. Now let's keep working on our Fnet x equation. We want to solve for the coefficient of kinetic friction, so we'll rearrange and isolate for mu k. Now looking at this equation, we know the mass of the box, we know the acceleration due to gravity, and we know the angle of the incline. What we're missing is the normal force. How do we find the normal force? Well, we set up an Fnet y equation, which is the sum of all the forces acting along the y-axis. So we have Fnet y is equal to the normal force minus the y component of the force of gravity. And now we can replace Fnet y with 0 because the box is not moving up or down along the y-axis. And then we can rearrange and isolate for the normal force. And we see that the normal force is equal to the y component of the force of gravity. And remember, we just learned that the y component of the force of gravity is equal to mg cos theta. And now we can replace the normal force with mg cos theta. And now we have everything we need to solve for the coefficient of kinetic friction. All we have to do is plug in our values. And what we find is that the coefficient of kinetic friction is 0.6. And that's the answer to our fourth question. And now let's move on to our fifth and final question. Here we have a hanging spring, and we are told it's stretched by 20 centimeters when a 5 kilogram weight is attached to it. And we want to determine what is the spring constant. Now the first thing I want to do is draw a free body diagram. I'll draw a point to represent the weight, which we know has the force of gravity pushing down on it and the spring force pulling back up on it. And we also know that the net force acting on this weight is equal to 0. And that's because it's not moving once it's been stretched. The next thing we want to do is write our Fnet equation. So we would have Fnet is equal to the spring force minus the force of gravity. We can replace Fnet with 0. And we can replace the spring force with negative kx. And of course, we can replace the force of gravity with mg. Now we were asked to solve for the spring constant, so we will rearrange and isolate for k. And we find that the spring constant is equal to negative mg divided by x. And now let's plug in our values for the mass, the acceleration due to gravity, and x, which is the displacement from equilibrium. And now first, I always convert x to meters, so we have 0.2 meters. But you might be wondering why it's negative 0.2. Well, you can imagine we have our spring, and we know it was stretched when we added a weight to it. If we assign its original unstretched position as 0 centimeters, and we imagine we have a number line, we're moving down below 0. That means our final position is negative 20 centimeters. So x is negative 0.2 meters. And now all we need to do is do the math, and we find that the spring constant is equal to 245 newtons per meter. And that's the answer to our fifth question. And now I hope you were able to solve each of these questions on your own using what you learned from the forces unit. And that's the end of our forces practice quiz.